This is my replication of the economic evaluation or cost effectiveness study in Journal of the American Medical Association Pediatrics from spring of 2018, published in spring of 2018. What they do a little differently in that article is they set willingness to pay equal to 0. They're comparing offering a vaccine to everyone and offering a vaccine to no one. And their main finding is that you should recommend the vaccine to everyone, that it's cost saving and it generates an effect. So not offering the vaccine to everyone was the dominated option. And the result of the economic evaluation on vaccines is basically that a vaccine is a slam dunk, that it saves money for gaining additional quality adjusted life years. So you don't even need to be willing to pay anything to do it. You would always recommend it because you're spending more and getting less. So it's actually saving money, generating quality adjusted life years. No vaccine is a dominated option. You would always choose vaccine or offering the vaccine to everyone as opposed to offering the vaccine to no one. So willingness to pay in this model will use what they use in JAMA Pediatrics article. The publication is where they just say willingness to pay of 0. So we're testing the hypothesis that a vaccine is cost saving as compared to not offering the vaccine to everyone. Now, if you remember from the last set of slides where we started coding up distributions. So remember there's 3 levels of detail you could put in the economic evaluation or cost effectiveness models. You could put just data, just numbers, like we started with. You could put variables and do sensitivity analysis, a deterministic sensitivity analysis with variables. The highest level of detail we'll do is, for now, is a distribution. So we're going to code up distributions for the cost of offering vaccines and for the effects of offering vaccines. And the distributions are going to unlock new graphs and new types of sensitivity analysis. The distribution, you're modeling the probability that something is cost effective and the probability that something is costly, the probability that it's effective. So when you model those underlying parameters as distributions, as probability distributions, then we'll be able to do a probabilistic sensitivity analysis and get some variation in the ICERs, look at the probability that offering the vaccine to everyone is cost effective. So in the project on screening, you remember my screening slides, I just had a cost distribution. Now I'm going to need a cost distribution and an effect distribution because we're going to look at both those dimensions in terms of probability. So distribute cost, distribute effect, and then we could look at probability distribution or a range of costs and a range of effects for vaccine as compared to no vaccines. When you code a distribution in TreeAge, sometimes you might want to use the same distribution for multiple variables or create functions that include those distributions. So I don't know if you have to in this case or not, but I'm just going to create variables and set those variables equal to the distributions. That way you could reuse the distributions as needed. And you could expand the cost variables and the effectiveness variables beyond just being equal to the distribution, if needed. So really simple here, we already created distributions for the costs and effects of offering a vaccine to everyone, and now we'll create variables for the costs and effects of offering a vaccine to everyone. For simplicity, we'll just say that the variables are equal to the costs, so we're distributing costs and effects. In the screening example, we only distribute costs. In this vaccine example, we'll distribute both the costs and effects. And then we'll look at some additional data visualizations you could gain from distributing both of those dimensions, cost and effect, rather than only distributing one or the other. Our model is going to be choosing between 2 choices, just like they do in JAMA Pediatrics, offering the vaccine to no one versus offering the vaccine to everyone. They have some other scenarios in the article where you're offering vaccines to children of certain ages. To simplify it, we'll just use offer it to everyone or offer it to no one, which is the first scenario that they talk about in their visualizations and the published readings, course readings. So after that blue square of the decision, you're choosing between vaccine which has cost and effect distributions, and no vaccine, which is a placebo. So no vaccine, we're saying it's minimal cost, minimum quality, sort of a placebo policy option there, not to vaccinate, not to offer vaccine to no one. Offering vaccine to no one is the dominated option here. You can see that red square, no vaccine, that's dominated. It's got the blue square identifying that as dominated. So you choose vaccine, which is on the lower right. You see vaccine has an effect of 0.03 and a negative cost. So you're saving money and you're gaining effect. So you would recommend the vaccine. Now remember, the net monetary benefit calculation incorporates the willingness to pay. This net monetary benefit is a little different here. Remember that we set willingness to pay equal to 0 in the model. Usually we set willingness to pay $50,000. In this, because we're testing for this cost saving feature and the dominated feature, we'll set willingness to pay equal to 0 and then calculate the net monetary benefit from there. Remember, you only use the top panel of that table. You exclude the dominated options. If it's dominated, it's no longer in the choice set. And when you solve the model here in the base case, you can see that vaccine, we're going to save $35, gain 3 quality adjusted life years. So it's going to choose that option where you're saving money and gaining qualities. That's why it snips off the no vaccine branch in red and highlights the vaccine branch in green, recommends offering it to everyone. How do we evaluate the probability distributions that we coded for the costs and effects of vaccines? We use a Monte Carlo simulation or a probabilistic sensitivity analysis. This is like we're studying, a thousand different vaccine policies. And we're going to take a random sample of 1,000 vaccine interventions from the underlying population of infinite vaccine recommendations. We're going to evaluate the model for a random sample of 1,000 vaccination interventions. Remember, we distributed the cost, so now it's going to distribute the effects and the monetary benefits. We asked for 1,000 simulations. There's 1,000 data points right there. So this looks like the graphs and the readings. I'm going to add the chart here to make it the scales the same as the graphs in the readings, just so you could see where the cost effectiveness is coming from in this data visualization. What I'm doing with the access scales is I'm setting them equal to the scales in JAMA Pediatrics. And you could just enter the minimum and maximum values for the x-axis and the minimum and maximum values for the y-axis and edit the chart to match the scale of JAMA Pediatrics. I tried to make the data replicate the results in the study as well. I cleaned up the data a little more, so our result is going to be a little more clear than what they found in the study. So this looks like the graph that you have in JAMA Pediatrics article. So we have 4 quadrants of the graphs. This lower right-hand quadrant where all the data is, that's the cost-effective quadrant. In the lower right-hand quadrant, cost is negative. The y-axis is negative. The x-axis is positive. So you're saving money and gaining effects. Those blue points are 1,000 randomly selected vaccination programs. And that circle is called a confidence ellipse. Remember from analytics or biostatistics that a confidence interval is 95% of your confidence intervals include the true value. This is an expansion of an interval to a confidence ellipse. 95% of the confidence ellipses are going to include the true cost effectiveness value. So that circle includes 95%, 950 data points of the 1,000 randomly selected data points that we did. The main takeaway from this graph is that it's always cost effective. We simulated 1,000 programs. They're all cost effective. 95% of them are in that confidence ellipse. The confidence ellipse falls entirely in that bottom right-hand quadrant. The bottom right-hand quadrant is cost saving, quality generating. So for all 1,000 of them, we're going to recommend the vaccine program as compared to no vaccine. Because it's a random sample, you will get a little different pattern each time you run it, or for each person who does it. But the variation should not be enough that it would dramatically change the result based on how many times you do it. But you could increase the number of samples from 1,000 to 1,500 and smooth it out if you want to, and try different numbers of simulations, and you could change the standard deviations and more or less variability to these functions.